we are, I can't speak, we are on day 3 of quadratics, and we're going to look at inverse of quadratic functions. If you recall from our functions unit that the inverse of a function is the reflection across the line y equals x. It is the reversal of the domain and the range, and we can find it by exchanging x and y values in the equation. It may or may not result in a function. So, specifically looking at a quadratic, we have y equals x squared minus 4 parabola that has a vertical translation down 4, so we're going to draw it. So regular step pattern, over 1 up 1, over 2 up 4, over 3 up 9. There we go. There. Y equals x squared minus 4. We're going to draw the reflection about the line y equals x. So it's not going to be perfect because we're sketching. But notice that I was a distance of 4 this way. So if I'm reflecting across the line y equals x, my starting point will be 4 this way. So my vertex is there. Reflection would be and I am trying to mirror image as best I can about the line y equals x. If I were to fold along the dotted line, my blue one should morph into my green one. Yes, it does look like a reflection about the line y equals x. Notice that my green graph is not a function. If I were to draw any vertical line, there we go, would hit the graph in 2 places. It is not a function. Graphing can be suspect at best, so let's find the inverse of this function by exchanging the x and y values in the equation. I'm going to start by drawing my original function just to verify by using our eyes. My parabola y equals x minus 1 squared minus 8 has a vertex at positive 1 minus 8. There we are. It doesn't have a vertical expansion or compression, nor is it upside down, so I use a regular step pattern to draw this. Over 2 up 4. That's enough to get me started. There, you notice I still hold my breath. All right, there's our original function. Let's exchange the x and the y values. So if my original function was this one, my inverse function, may not be a function, my inverse relation, I can obtain that by swapping my x and y values in the equation. I'm going to solve for y so that I can see it written in the form that I'm used to. I'm going to add 8 to both sides. I'm going to impose a square root on both sides, but I must remember to consider the positive or the negative square root of both sides, and I will add 1 to both sides. There. That is the inverse of the function y equals x minus 1 squared minus 8. I would like to graph that. I can only graph one thing at a time. So the first thing that I'm going to graph is the positive part, which would be y equals positive square root of x plus 8 plus 1. And the second thing that I'm going to graph is the negative part, which would be y equals negative x plus 8 plus 1. Those two parts separately are each called functional arms, but together it's not a function. This will be the lower functional arm. I'm assuming. We'll see when we draw it. Okay, the first one. The parent function is the square root of x. I know how to draw that. I know that it is a shift to the left 8 and up 1. 1, 2, 3, 4, 5, 6, 7, 8, up 1. Regular square root pattern, no vertical compressions or expansions, and so on. So I will draw it. There. That is the upper functional arm. Y equals the square root of x plus 8 plus 1. The lower functional arm is the vertical reflection of the square root function, and then move to the left 8, up 1. It would be the upside down of what I just drew. And we can see that it does indeed appear to be a reflection across the line y equals x. Both green parts together are indeed not a function. And we label those as the upper functional arm and the lower functional arm. There. Thirdly, find g of x, which is the inverse of f at x equals 2x plus 3 squared minus 4, and state the domain and range of g of x. All right, I'm going to start with f at x. I would like to draw it, and I would like to state its domain and range. So for f at x, I have a vertex of 3 to the left, down 4. I have a vertical expansion, factor 2, which means my step pattern has been doubled. It is upwards. So over 1 up 2 instead of 1, over 2 up 8 instead of 4. There. That is my original function, f at x. Sorry, a little off there. There, f at x. We know from our functions unit that the domain of f at x is x can be any real number. It will expand horizontally to the left and to the right eventually as x increases and decreases. The range for the parent function would be y greater than or equal to 0. Y is a real number, but this one has been shifted downward 4. So our y is greater than or equal to negative 4. Y is a real number. Let's look at g at x now. G at x is the inverse. So for g at x, I'm going to change the y and the x values of my original f at x. So for g of x, x equals 2 y plus 3 squared minus 4. I'm going to rearrange it into the form that I'm used to, y equals. So let's add 4 to both sides. So inverse order of operations to isolate y. Going to divide both sides by 2. Impose a square root on both sides, remembering to consider both the positive and the negative possibility for that. And lastly, I'm going to subtract 3 from both sides. So y equals positive or negative square root of x plus 4 over 2. Take away 3. I would like to draw that, and it is a fine equation the way it's written, but I'd like to change it just a little bit for ease of graphing. Positive or negative, which I can only do one at a time, square root of, I'm just going to write that as a half x plus 4. In order to graph that, I'm going to do the positive functional arm first. So I'm going to do the positive square root of a half x plus 4, take away 3. That is a horizontal expansion, factor 2, for the square root function. It will be left 4, down 3. My square root function, horizontally compressed, or expanded, factor 2. means all my overs are doubled. I would normally, from my original starting point, which is left 4 down 3, right here, I would normally go over 1 up 1. Now I'm going to go over 2 up 1. To get myself a little more anchored, I'm going to do one more pair. I would normally go then from the original starting point over 4 up 2. I'm going to go over 8 up 2. There. That is my upper functional arm. Y equals positive square root of a half x plus 4 down 3. There we are. My lower functional arm will do everything the same except that there is a vertical reflection upside down. It would be what I have drawn before, but downwards. And that upper and lower arm together should look like a reflection across the line. Y equals x. The two parts together are not a function. We can write it separately as two functional arms. Notice that the domain and the range for g at x are rather different than the domain and range for f at x. Just by looking, the domain appears to start here and move everything to the right. So there is no domain over here. So my domain is x greater than or equal to -4, and it's a real number. The range appears that it will eventually go vertically, upwards and downwards forever. It would be y is an element of the real numbers. Notice that the domains and ranges are opposite between inverse functions. That is part of the definition. Domain and range have been exchanged. Last example is a word problem with really nasty numbers. The rate of change in the surface area of a cell culture can be modeled by the function s of t equals -0.005 t minus 6 squared plus decimal 1/8, where s of t is a function of the surface area in terms of the time, which is in hours. State the domain and range of s at t. The domain is our t values. They've already given us our t values. 0, less than or equal to 12, less than or, there. And all the bits in between. Our range is our function values. And it would make sense that the smallest surface area of a cell culture would be 0. And the largest surface area of a cell culture would come from the vertex, which is 6.18. The y value of the vertex is 0.18. That would be the largest surface area of the cell culture, with all the possibilities in between. We have been asked to determine the model that describes time in terms of the surface area. So perhaps if we knew the surface area of the cell culture, we would know how long time had passed. Could be very helpful. So our goal is to come up with t in terms of s. That's the inverse function, x in terms of y, in other words. I wouldn't change all my letters to x's and y's. I would leave it the way it is. The original function is s of t equals, I'm just going to write s equals -0.005 t minus 6 squared plus 0.18. If I want the inverse function, I'm going to solve now for t so that I can write t equals, and it will be t in terms of s. So I am just going to rearrange this question the way it is to isolate for t. I am going to subtract 0.18. Inverse order of operations, I would divide by -0.005. I would take the square root, impose the square root on both sides. And then lastly, add 6. And I don't know if I would write it any fancier than that. There. We have t as a function of s just by rearranging the equation and solving for the other letter. We have an inverse function. If it is an inverse function, our domain and range should be opposite. The domain is the input values. So your domain would be your s values. So although we would write it as we did above, s is between 0 and 0.18, that used to be what our range looked like. It is now the same letter, but it is under domain. It has been exchanged. The range is the letter T, and it looks like what the domain used to look like. If your range and domain have been interchanged, it is an inverse function. Try page 160, numbers 2 to 8, 10, 11, 13, and 15. No course notes.